In sections 9.3 and 9.4, we're going to learn several tests that we can use to determine whether a series converges or diverges. And we're going to start off with the integral test. The integral test is this. Okay, if f is positive, continuous, and decreasing when x is greater than or equal to 1, and a sub n is equal to f of n, then summation of n equals 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx, these two things either both converge or both diverge. Okay, let's look at an example of how we can use this. So I have a summation n over n squared plus 1. And I want to know whether this converges or diverges. So to see, I'm going to look at the associated integral. So I'm going to have f of x is equal to x over x squared plus 1. And we know that this is positive and continuous for x greater than or equal to 1. Now we have to decide, is this decreasing? So we're going to look at the derivative. F prime of x is equal to x squared plus 1 times 1 minus x times 2x over x squared plus 1 quantity squared. Okay, and I can simplify that to negative x squared plus 1 over x squared plus 1 squared. So this tells me if x is positive, f prime of x is going to be less than 0 when x is more than 1. Okay, if x is greater than 1, that's going to be positive, and then the negative means that the derivative is going to be negative and the function will be decreasing. So we've met the conditions for the integral test. Now let's integrate. And this is equal to 1/2 of 2x over x squared plus 1. I took the 1/2 out so I could have the 2 in here. Which is 1/2 of the limit as b goes to infinity of the integral from 1 to b, 2x over x squared plus 1 dx, which is equal to 1/2 of that limit as b goes to infinity of natural log x squared plus 1. And we're going to evaluate that from b to 1. We get 1/2 of the limit as b goes to infinity natural log b squared plus 1 minus the natural log of 2. And of course, this, as b goes to infinity, this whole thing goes to infinity, which means that both the function and the series diverge. Let's look at another problem where we can use the integral test. Now the summation is n equals 1 to infinity of 1 over n squared plus 1. Okay, so my associated function would be f of x is equal to 1 over x squared plus 1. Okay, we know that this is positive when x is greater than 1. We know that it's continuous. And we know that it's decreasing. As x gets larger, the value of the function is going to get smaller. So we've met all of our conditions. So now let's integrate. So there's our integral. The limit as b goes to infinity of the integral from 1 to b of 1 over x squared plus 1 dx. And then when we integrate, we get the limit as b goes to infinity of arctangent x evaluated from B1. We got the limit as b goes to infinity of arctangent b minus arctangent 1. And then this is going to be pi over 2 minus pi over 4. So it's just going to be pi over 4. So we can see that because the integral converges, that the series also converges. Before we do our next example, I want to introduce another kind of series called the p-series. And a p-series has this format. One over n to the p power. In this case, the p is a constant, and we're just going to increase the values of n. So this would be 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, and so on. Okay. A specific case of this is called the harmonic series. And a harmonic series n equals 1 to infinity of 1 over n, just 1 over n. So in this case, p equals 1. And this is 1 over 1 plus 1 over 2 plus 1 over 3, and so on. Okay? And the harmonic series has important applications in the field of music. Let's look at some different p-series. We'll start with that harmonic series. And we know that this is, we just wrote this, 1 over 1 plus 1 over 2 plus 1 over 3, and so on. And so we know that p equals 1. And theorem 911, which is in your textbook, tells us that this converges if p is greater than 1, and it diverges if, make a little more space here, if p is greater than 0 but less than or equal to 1. Okay, so in this case we know that p equals 1, so that fits this condition, and this diverges. Now if we look at the second one, 1 over n squared, we see here that p equals 2, And so now we're up here in this condition, and we know that this one converges. If we were to write out this sum, we would find that the sum is equal to pi squared over 6, which is approximately 1.645. But the integral of the associated function is equal to 1. So even though both the integral and the summation converge, they don't necessarily have the same numerical value. It's an important point to remember. Okay, let's test another series for convergence. Okay, this is similar to the harmonic series. Okay, if the terms were greater than the harmonic series, then we would expect it to diverge, but they aren't. So let's look at our associated function. We know that this function is positive for x greater than or equal to 2. Now we need to determine, is this decreasing? So we're going to rewrite this function as f of x is equal to x natural log x to the negative 1. And then we'll find f prime of x, which is equal to negative 1 times x natural log x to the negative 2 times 1 plus natural log x So we could rewrite this all together as negative 1 plus natural log x over x squared natural log x squared. So now we can see that this is less than 0, so the function is decreasing when x is greater than 2. So we've satisfied the conditions for the integral test. So let's integrate. And this goes from 2, not 1. So we're going to move this x up here. So I have 1 over x over natural log x dx. It's going to be the limit as b goes to infinity. The natural log of x evaluated from 2 to b. Then I have the limit as b goes to infinity, the natural log of b minus the natural log of 2. And this is infinite. So because this integral diverges, the series also diverges.